So what we're looking at today are acid-base reactions. Okay, so we've looked at the reactions between acids and water and between bases and water. We've looked at sort of strong and weak acids and what that means. Okay, but today we're going to look at two different types of acid-base reactions. All right. So the first one we're going to look at is just the reaction between an acid and a base. Okay, pretty straightforward, probably pretty important. Okay, so we've got a bit of a template here. So an acid and a base, when they react, okay, so an acid is usually, these are both usually sort of ionic compounds, okay? We've seen that they can be molecular compounds like hydrochloric acid, but we've seen that this is effectively and this can be kind of, compared to an ionic compound by this sort of thing, all right? So we've seen that these are both ionic compounds, okay? For this reason, what's going to happen, and we've seen that they can both sort of donate and receive protons, hydrogen ions, okay? And so what's going to happen here is we're going to have a salt and water produced, okay? Now what this means, as you may or may not know, a salt is basically just an ionic compound, okay? The word salt really just refers to an ionic compound, okay? And so we're gonna when we have an acid and a base, okay, there's gonna be some hydrogen or there's gonna be some hydrogen floating around, some hydroxide, whatever, in the acids and the bases, okay. And what's going to be produced is a water molecule, okay. And what's the leftover ions, the ions that aren't sort of donating protons or being received by protons, or the ions that aren't getting mixed up in the production of this H2O molecule, are going to end up forming the salt, okay. And so we're going to do an example in a minute, okay, but I just want to look at one particular case, okay. So if we have an acid and a base, okay, and if the base is a carbonate, okay, so if we have an acid, so if we have an acid and so we know that carbonate, so for example, sodium carbonate, can act as a base, okay, because carbonate is a basic ion, alright? However, what we're going to do here is look at what happens when an acid reacts with a carbonate, so an acid and a base, but a certain type of base being a carbonate, okay? So yes, carbonate is a base, but okay, it's a special type. So we've got a carbonate here. Okay, so if we look at hydrochloric acid reacting with this carbonate, okay, we know that a salt is going to be produced. In this case, it's going to be sodium chloride, okay, plus, okay, and now here, this is an acid and a base reaction, alright, this is the type of reaction sort of that we've looked at up here, except, okay, there's no way here for the acid and the base to just directly produce water and a salt, okay? There's no way for this acid and this carbonate to produce a salt and some water, okay? It just doesn't work, okay? Now, if we do this properly, we can look at this and we can balance it. We can chuck a 2 there, so we've got 2 sodiums and 2 chlorides, and a 2 there. And then what we're left with is carbonic acid, okay, this substance here. Okay. So this is the reaction between, so acids and bases usually produce a salt and water, but here they don't. They produce a salt and they produce this carbonic acid, okay? Now what's essential in here is that you're not expected to know this, but a carbonic acid actually undergoes a reaction with itself, kind of dissociates by itself. So if we have carbonic acid, okay, and I haven't been writing the states up here, okay, but you can't forget to do that. I haven't written the states there, but it's very important. So we've got carbonic acid here, okay, and what happens is, well, this could be, I guess technically this should be a partial reaction arrow, so like this, okay, but it occurs to a very large extent, okay, and what we have is that it produces water, and carbon dioxide, okay. So when we have carbonic acid, okay, it nearly completely reacts. It doesn't quite. We've got this partial area here, but it nearly completely reacts to produce water and carbon dioxide. Okay, for this reason, having this equation here doesn't really make sense because, yeah, we're going to produce carbonic acid, but, you know, it's going to react away by itself to produce water and carbon dioxide. Okay, for this reason, what we do is we rewrite this as 2 hydrochloric acid molecules. So I'll include the states this time. And sodium carbonate produce 2 sodium chlorides. So this should be aqueous. And this should be aqueous. Okay, and instead of writing carbonic acid here, we know that carbonic acid is pretty much going to completely turn into these two. So we're going to replace carbonic acid with water and carbon dioxide. Okay, so as you can see here, so now we've got the hydrochloric acid and this sodium carbonate base. So we've got an acid and a base, but they're not producing a salt and water. They're producing a salt and water and carbon dioxide. Okay, so basically we can interpret this equation 1. Okay, so that's one sort of template for an acid-base reaction when the base, okay, is not a carbonate. Okay, so we took looking at that template kind of applies to all equations where the base is not a carbonate. Okay, and so that means we've got a different sort of template for when we're dealing with a carbonate, for when we're dealing with an acid and a base, and the base is a carbonate. Okay, so we've got this second template here. Okay, so we're going to say an acid and a base, and not a base, and a carbonate. So this is a base, but it's a special type, it's a carbonate. Okay, and what's going to happen is that we're going to have a salt. So again, this is an ionic compound, as we've talked about above. So this is a salt, and it's going to produce water, and it's going to produce carbon dioxide. Okay, so that's the difference. Okay, we've got an acid and a base. Okay, and when that base is sort of anything but carbonate, it's going to produce salt and water. When that base is a carbonate, it's going to produce salt and water and carbon dioxide. Okay, and what's important here is that, yeah, we've talked about the idea of, you know, strong acids and strong bases reacting completely, and weak acids and weak bases reacting partially, and so that's where we introduced these arrows. All right, but in this case, where we have acids and bases reacting with one another, okay, it's a slightly different situation. If we have an acid and a base reacting with each other, yeah, sure, a weak acid may be a little bit unenthused to react with water, you know, it might only react partially, okay, but when we have an acid and a base reacting together, they're both just enthusiastic enough, okay, and you could sort of say they're both keen enough when they're combined to react completely, okay. By themselves, this weak acid and this weak base are only going to react partially, okay. They're not that excited to do it, but once they get together, they're both pretty excited, okay, and so they're both going to react fully when they're reacting with one another, okay. And so that's why when we're talking about acid-base reactions, or as a sort of a subcategory of that, an acid-carbonate reaction, we're going to use full arrows, okay. These reactions occur to completion, okay, because when they're around each other, they get a little bit more excited and keen to react than when they're just reacting with water. They're not that excited. They only partially react. Okay, so we're going to look at an example down here. We're going to write an equation for the reaction between potassium hydroxide and phosphoric acid. Okay, so potassium hydroxide is the base here. Phosphoric acid is obviously the base. Is obviously the acid. Okay, so we look this base, potassium hydroxide. It's not a carbonate, so we can follow template 1. Okay, follow template 1 for this example. So that means we've got an acid and a base, so we've got phosphoric acid. Okay, whenever we see acids and bases, we almost always assume, unless we're told otherwise, that they are in solution. Okay, plus potassium hydroxide. So these are the two reactants we've been told this. We're just kind of copying down these formulae. All right. Okay, and what are they producing? Okay, well we know they're going to produce a salt, and they're going to produce some water. Okay, and so if we look at this, we've got a hydroxide ion here, and 3 protons here attached to the phosphate ion. So we've got a phosphate ion there, a PO4 3-. That's a phosphate ion. Okay, and we got 3 H pluses. So this is almost what we do when we're getting prepared to write an ionic equation. We're just trying to figure out what the ions are, okay, and see how they're going to intertwine with one another, how they're going to behave around each other. Okay, so we've got this set up here. Okay, and we know that water is going to be produced. We know that salt and water. We know that water's here. And now we just need to figure out the chemical formula for the salt that is going to be produced. So we know that it's a salt, but we don't know what the salt is. Okay, but we know that we've produced water here. Okay, and we can sort of look around here and see that there's a hydroxide ion here and a proton here, and we know that they like to come together and produce water molecules. Okay, so what we're going to do is we're going to get rid of that, and say there's 2 protons left over. Okay, and say that so what we've done here is we've said that 1 proton here has combined with the hydroxide ion to produce the water. Okay, so what we're left over is 2 protons here, and then obviously the phosphate ion and the potassium ion. Okay, so now we can see that this is 3-, and then we have 3 positive charges here, and so what we're left with is basically a dihydrogen phosphate ion. Okay, that's how we can look at this. We can look at these as being one thing together. Okay, dihydrogen phosphate ion and a potassium ion. Okay, and now evidently these are 2 ions. They've got opposite charges that will cancel each other out. So the salt that's produced is going to be potassium dihydrogen phosphate. Okay, it's a pretty complex sounding name, but it's pretty straightforward once you realize what it is. We've got potassium. That's the cation, the positive ion. Okay, and it's dihydrogen phosphate. Alright, so that's sort of a formula that you could use for potassium dihydrogen phosphate.